Hello everyone, welcome back to my channel. In this video, let me tell you how to model a source for a power system studies. To model a source, we need to collect certain input data from the customer. The source voltage, 3-phase fault MVA and single-phase fault MVA of the source and its X/R ratio. In fact, both the 3-phase fault and single-phase fault. I have chosen line-to-line voltage as 220 kV and 3-phase fault MVA 6313 MVA and single-phase fault MVA as 5000 MVA for both 3-phase and single-phase fault. 11 chosen as X/R ratio. With this input data, I am going to model a source and validate the same using different softwares. For modeling a source, we need to understand positive, negative and zero sequence impedance. Initially, I am going to calculate positive sequence impedance, that is positive sequence resistance as well as reactance. In order to calculate positive sequence impedance, we must know 3-phase fault current. 3-phase fault current may be computed from 3-phase fault MVA and line-to-line voltage. So we know the 3-phase fault MVA and line-to-line voltage. Substitute those values in the formula. You may get 3-phase fault current as 16.567 kiloamps. And I am going to calculate phase voltage, which is computed from the line voltage. So the phase voltage is 127.021 kilovolt. Then the positive sequence impedance is phase voltage divided by 3-phase fault current. Substitute both this value. You may get positive sequence impedance as 7.67 ohms. Further, I want to calculate positive sequence resistance and reactance. We know that positive sequence impedance is equal to square root of R1 square plus X1 square. R1 is positive sequence resistance, X1 is positive sequence reactance. And also from the input data, we understood that X1 by R1 is equal to 11. So from this, we may get X1 square as 121 R1 square. Substitute this X1 square in Z1 formulae. You may get Z1 as square root of 122 R1 square. From this, it is very easy to find out R1 value. And once you got R1 value, you can easily calculate X1 since we know X1 by R1 is 11. So we can easily find out R1 as 0.694 and X1 as 7.6355 ohms respectively. Then, in addition to positive sequence impedance, as I mentioned earlier, we are supposed to find out zero sequence impedance, that is zero sequence resistance and reactance. In order to calculate zero sequence impedance, we need single phase fault current. The single phase fault current may be computed from single phase fault MVA and line-to-line voltage. Substitute those values here in this formula and find out single phase fault current as 13.122 kiloamps. So also we know that single phase fault current can be computed from 3 times of V phase divided by sum of positive sequence, negative sequence and zero sequence impedance. Our objective here is to calculate zero sequence impedance. So rewrite this equation so that you may find out zero sequence impedance, where we need phase voltage, single line to ground fault current and positive negative sequence impedance to calculate zero sequence impedance. In fact, we will assume positive sequence impedance as negative sequence impedance so that your Z0 value may be computed as 13.70 ohms. As usual, Z0 is square root of R0 square plus X0 square. And also from the input data, we know that X0 divided by R0 is 11. Hence, X0 square is 121 R0 square. Similarly, we can calculate R0 and X0. We have computed R0 as 1.24 and X0 as 13.65 ohms. So once we computed positive sequence impedance and zero sequence impedance, in fact positive sequence impedance is same as negative sequence impedance, we can simply model a source. So this is your positive sequence resistance and reactance we have computed, and the same positive sequence resistance reactance may be calculated in terms of different unit, since different softwares use different units. Say for example, ohms value may be preferred in PSCAD software, and per unit value preferred in PSSE, and ETAP may be represented with percentage value. So by simply taking base kV and base MVA, base kV as 220 and base MVA as 100, we can simply calculate R1 X1 value in terms of per unit. Then multiply these values into 100, so you may get percentage value. Similarly, we can calculate zero sequence resistance and reactance. So we already computed this value, and by considering base kV and base MVA, convert this ohms into per unit, you may find these values. And for these parameters, we have computed these values. Let me straight away go to ETAP. Let us model the source and cross verify the result. A rating, you choose 220 kV, short circuit, 11 XBR ratio for both single phase and three phase, 6313 is three phase faulty MVA, 5000 is single phase faulty MVA. Have a look at this positive sequence resistance and positive sequence reactance provided in terms of percentage. In fact, positive sequence, negative sequence, both the values are same. And look at zero sequence. Let me go to our calculation. Let us validate these results. We got the same result. Then, now to run the short circuit analysis. So you can see that 16.567 kiloamps is coming out of this source. This is three phase fault. Let me go to a line to ground fault. Line to ground fault is 13.122 kiloamps. This is what we observed here for a single phase fault current, whereas three phase fault 16.567. We go to PSCAD just to take down the source in one bus bar, create a fault at bus bar. I'll go to this configuration. So 100 MVA is base MVA, base voltage is 220 kV, 50 Hz frequency. I'm considering this as zero sequence impedance. Differs from positive sequence impedance, yes, because we have two values, one for positive sequence, another one for zero sequence. So I'm giving this input in real and imaginary format because both the values are in terms of ohms. Okay. We can also have option here to provide both these values in terms of magnitude and angle, but as of now I'm having a real and imaginary value. Then coming to positive sequence impedance, whatever the value we have calculated in terms of ohms, I have substituted here. Zero sequence impedance, the same calculation the results what we found here is available, and I already ran this model and found a single line to ground fault here, 13.122. Have a look at this. A to G line to ground fault is applied here. I'm getting this 13.122. I can also cross check this fault type with the three-phase fault. Let me run this model. Now you cross check this one. It is 16.54. Sorry, 16.564. So even PSCAD produces the same result when we properly model this particular source. And again, I'm going to PSSE now. So I have chosen a grid where the source value in terms of per unit, R and X in terms of per unit I have entered here, and short circuit values tab with the positive R. I am choosing subtransient, transient and synchronous. All the values are same. And this negative sequence value, which is same as positive sequence value. Zero sequence as we computed in the calculation I have provided here. So now run this short circuit. So three-phase and line to ground fault, single line to ground fault running on all the buses. In fact, only one bus I have. Close this. View the output. So you can see the output. The fault MVA is 6312 for three-phase, approximately 5000 for single line to ground fault, and 16.56 kilo amps for a three-phase fault current and 13.12 for a single phase. Okay. So this way you may conclude the validation of your results. I hope this helps you to understand how to model a source for a power system study in 3 different software. Thank you.